All right, let's go ahead and pick up on our solving one variable linear equations and inequalities, and let's investigate. So I want you guys to first take a minute to pause the video and make sure that you have completed all tables on the front side of the paperwork. Once you've got that, go ahead and press play, and let's see how we did. So as we take a look at our tables, we want to compare our inequalities to equations. And we've talked in the past that a big difference is an equation can have one solution, no solution, or infinite solutions, whereas an inequality has a range of solutions. So as we look at 3x is less than or equal to 6, we see that that is a true statement for when x is -1, 0, 1, and 2. So because those are the values that make it true, on an inequality, we shade our possible solutions. Therefore, our correct shading would be the one on the right, because 9, 12, and 15 are not solutions. So we would shade in the 2 because it's included and darken in that arrow to show that it goes on forever. So it is any value equal to 2 or less that makes it a solution. Now, could we have just done that by solving the equation format, kind of like we do? Let's take a look. If I take 3x is less than or equal to 6, using our inverse properties, we know that to undo multiplication, we would use that division property of equality, and that would give us x is less than or equal to 2. Isn't that the same thing that we just graphed? So solving an inequality can be the same as solving an equation. Let's take a look at this next example. So now we have -2 is greater than -4. And we see for this one that our solutions of -3, -4, and -5 are the ones that make it true. However, -2, -1, 0, and 1 do not. So therefore, -2 is not included, which would be an open circle, but it's everything less than -2. So again, we're looking at the one on the right side. Anything larger than -2 was not a solution. So now let's take a look at solving this similar to how we would an equation. To isolate the variable, again, to undo multiplication, we would divide both sides by a -2. And that's going to leave me with x is greater than -2. Well, wait a minute. Did we just find out that that was the true statement? What happened when x was greater than -2? At no point in time did any of that work. So therefore, that can't be true because x was actually less than -2. So let's hold that thought. Moving on to our next tables. For the next one, we found that the values of 2, 3, 4, and 5 all made the statement true. So therefore, this time, 2 is included, which would mean that it is shaded, and it was everything larger than 2. So here would be our solution to the inequality with the graph, because anything that was 2 or greater makes that inequality true. Now let's look to solve it as an equation. My inverse operation to division is to multiply both sides by 2. That'll cancel that out, and that gives me x is greater than or equal to 2, which is the same thing that we had here, making a true statement. Taking a look at our third one. Now we see for this one that our statements of x equals -1, 0, and 1 work. Anything less than that -1 did not work. So -2 is not included, which would mean it would be an open circle, but it does include everything larger than -2, which would represent this graph. with all of our range of possible solutions. Let's go ahead and solve that as an equation. Using my inverse operations to undo division by -3, I would times both sides by -3. That's going to cancel, and that's going to leave me with x is less than, as I write -3 as a fraction, that would be -3/1, so that would give me -6/3, which reduces to -2. So as I take a look at my graph of our possible solutions, was x less than -2? And it wasn't. We found that x was actually greater than -2. So now here's what I want you to think about. We came up with proving all of our solutions. However, when we solved them mathematically, 2 of our answers came out wrong. And it happened to be when we were working with negatives in our inverse operations. Can you come up with a conjecture that would show us how it's different to solve inequalities compared to equations, especially when looking at those negatives? Take a minute to brainstorm, pause the film, then when you're ready, go and push play again to hear the outcome. All right, let's take a look. When we're working with negative values, keep in mind the whole purpose of an inequality is the same as an equation in that we're trying to create a true statement. So when we look at the inequalities here, if I take and I add -2, whatever we do to one side, we do to the other, and that's going to end up giving me 2 is greater than 0. Still a true statement, so that would be correct. If I subtract a -2 from both sides of an inequality, I'm going to get 6 is greater than 4. That inequality is still correct. Now let's multiply both sides by a -2. That gives me -8 is greater than -4. Now some people might not realize this, but when you look at that, is -8 greater than -4? And it's not. So in order to make that a true statement, we have to flip that sign. -8 is actually less than -4. And now it maintains a true statement by us flipping that sign. When we go to divide by a negative, let's divide by -2. And that's going to give us -2 is greater than -1. Again, -2 is not greater than -1. It is further away from 0 on a number line. But if we want to maintain the trueness of that statement by flipping the sign, -2 is less than -1, we now have our true statements. So folks, our conjecture, same but different. When we solve an inequality, we still use the same inverse operations that we use when solving an equation, but the part that is different, in order to maintain a true statement, anytime we multiply or divide both sides of the inequality by a negative, we must flip that sign in order to maintain a true statement. So same but different. We still use inverse operations, but remember, anytime you multiply or divide both sides by a negative, you must flip the sign. With this, let's go ahead and try some of those practice problems. Make sure that you have a great day today.